miniaturization in general, it is reducing the size. Okay, so these are the different aspects. So these are the different aspects where scaling can be applied. One is scaling in geometry. Okay, the other one is scaling in rigid body dynamics, scaling in electrostatic forces. As I said before, miniaturization need not be applied only to a physical object. You can also include few parameters, other parameters such as forces. Okay, you can reduce electricity, the level of electrical levels, then fluid mechanics, and also the heat transfer. So these are the various fields in which the scalings can be applied, and all these are very important in examination point of view. Okay, so now we'll go look into why these scaling laws are. Okay, so the present system, whatever we design, it should be intelligent, robust, multifunctional, and low cost. Correct? So these are the four important points of the system that exists today. The system should be intelligent enough, robust enough. Okay, that means it has to withstand all the hard parameters that is applied on it. It should perform some different functions at the same time, simultaneous functions it should perform. At the same time, the cost of the system should be economical. Along with this, there is one more necessity in today's scenario, that is the system should be portable. And in order to make the system portable, it is necessary to miniaturize or reduce the size of the individual components. That's why scaling laws is very important in it. Okay. So these are the types of scaling laws. As I said, this can also be the type scaling in geometry, rigid body dynamics, electrostatic forces, electromagnetic forces, electricity, fluid mechanics, and heat transfer. So we'll now concentrate on scaling in rigid body dynamics. Sorry, scaling in geometry. So in geometry, there are two important parameters. One is the volume represented by V and the surface represented by S and the mass represented by M. Okay. So we know that if L be the linear dimension of a solid, okay, we know that volume is equal to L cube, correct? And the surface area S is equal to L squared, where L is what? Linear dimension. So if I take the ratio of S by V, then I'll have L squared by L cube, which is equal to L to the power minus 1. Okay, so this is important. Now, how this rule will affect in miniaturization, we'll see. Okay, now there is a rule. What is that rule? Volume is proportional to L cube and surface is proportional to L squared. Okay, say for example, L, I'll increase it by 10 times, then volume is increasing by L cube, that is 1000 times, and the surface is increasing by only 100 times. Correct? So I repeat, if only L is increased by 10 times, then volume is increasing by 1000 times and surface area is increasing by 100 times. So the ratio S by V is increasing by L to the power minus 1. Okay. So if I take the surface to volume of an elephant, I'll get 10 to the power minus 4 by mm. That of a dragonfly, I'll get 10 to the power minus 1 by mm. Okay, so in order to see how this will affect the scaling, so this is a rule, okay, that is S by V equal to L power minus 1. How this affects in geometry, we'll have a example here. This example, it was solved in class, okay, before lockdown. I hope you would remember this. Okay, so here there is a question, what would happen to the required torque to turn a micromirror? So this is a micromirror. Okay, what would happen to the required torque? Torque is represented by tau here with a 50% reduction in size. So say for example, So if I apply a force, that force is nothing but a torque. Okay, let C, B, and C and B and T be the dimension of this micro mirror. If I apply the torque, then definitely this torque is moving in the anti-clockwise direction as indicated by this. Okay, then the question is, if I reduce the size of this object, that is, if I reduce C, B, and T by 50%, will the magnitude of the torque remain same? So, by our general understanding and common sense, definitely it won't, right? Because the same force would might not be required this time. Why? Because the size has been reduced. But what is that magnitude of the force reduced? That we have to calculate. Okay, so this is how we calculate. So first we'll establish a general relation, that is the torque is proportional to I by y, where I by y is the mass moment of inertia of the mirror. It is the moment of inertia of the mirror. So how to relate this I by y to a mass and the width of the mirror? See, the parameters given here are C, B, and T, but inertia should be related to these parameters C, B, and T. Then only we can solve this problem, right? So this moment of inertia is given by 1 by 12 into mass into C squared. Okay, where M is the mass of the mirror and C is the width of the mirror. Okay, now, but we only have here the parameter C, but what about B and T? So M can be related to this parameter C, B, and T by this equation. That is M equal to the mass density of the material into its area. That is B into C into T. Okay, substituting M equal to rho into B into C into T to this equation multiplied by C squared, I'll get Iyy equal to 1 by 12 into, in place of M, I'll substitute rho into B into C into T, and because of this C squared I'll have C cube here. Okay, so 1 minute. So I'll continue. So I have now established, I have represented the mass moment of inertia in terms of C, B, and T, that is the dimension of the mirror. Okay. Now the question says that the dimension is now reduced by 50%. That is B, C, and T individually they are reduced by 50%. Means what? B by 2, C by 2, and T by 2. Okay. So remember here, since there is a C cube here, substitute like C by 2 whole cube. It should be C by 2 whole cube. While solving the problem, if you write C cube by 2, then the answer you will get wrong. Okay, so the size here is reduced by 50%. See, initially it was B, now it is B by 2. The new dimension is B by 2. Initially it was C, now it is C by 2. Since there was a whole cube, it's a whole cube. Now it is T by 2. Okay, now the rho being a mass density is a constant, we'll take it out, and 1 by 12 it is also a constant. So I'll get the relation as 1 by 32 into 1 by 12 into B into C cube into T. So I will bring out to the initial equation, that is Iyy. So in total I'll get 1 by 32 into Iyy. Meaning if I reduce the size of this micro mirror by 50%, then the magnitude of the torque, that is the new magnitude of the torque, okay, it is reduced by 32 times. Understood? I hope you would have understood. This problem is very important. Okay, if the size of the micro mirror is reduced, then definitely by our general understanding, the micro mirror torque, okay, will also get reduced. But what is that magnitude? That magnitude is now given by this. Okay, that is the new torque is reduced by 32 times. So this is how these rules will help us finding out the parameters when the size of the object is scaled down. Okay, so this is scaling in geometry. So I repeat for those who have joined new. Quickly I'll repeat. We know that L equal to the linear dimension of a solid. So if L is the linear dimension of a solid, then V proportional to L cube. We know that S, that is the surface area, is proportional to L squared. So if I take out the ratio surface to volume, then I'll have L to the power minus 1. So this is the scaling laws in geometry. How this will help? So if I increase the dimension of the L by 10 times, then the volume will increase by 1000 times and the surface area will increase by 100 times. Okay, so we have the micromirror here whose dimension is given by C, B and T. Now, if this individual dimension is reduced by 50%, then the question is asked to find what is the torque of the micromirror. So first, we need to establish the relation, that is the torque is proportional to the mass moment of inertia. Now, this mass moment of inertia should be expressed in terms of C, B and T. For that, we have mass moment of inertia equal to 1 by 12 into mass into C squared, where mass is given by this equation. Substituting mass in this equation, I'll get Iyy equal to 1 by 12 into P into B into C cube into T. So if individual size is scaled down by 50%, so I'll get 1 by 32 of Iyy. That is, if the size is reduced by 50%, then the torque is reduced by 32 times. I hope this is understood. Okay. So now we'll discuss about the scaling in rigid body dynamics. Okay. So the second parameter, that is the scaling in rigid body dynamics. So here the dynamics means it will involve velocity and acceleration, and the initial forces for that are force, power and pressure. These definitions you should have known by your physics knowledge. Okay, what is a force, what is a power, okay, what is inertia, what do you mean by mass, and what is an acceleration, and what is time. Okay, so these definitions you should know. Followed. Now, first we need to establish the rules like this. Okay, so we know that F is equal to mass into acceleration. Okay, then the acceleration F is equal to mass into acceleration, and the speed can be given by the initial velocity into t plus half into acceleration into t squared. Okay, so where v naught is the initial velocity, if v naught is equal to 0, then I can express acceleration as 2 times of s by t squared. Okay, Rahul, 1 minute. Rahul dena. Okay, we'll continue. So I know that from Newton's second law, F is equal to mass into acceleration, and from the equation, kinematics equation, I know that acceleration is equal to 2 into s by speed by t squared. Okay, substituting this new value of acceleration in this equation, I'll get F is equal to 2 into s into m by t squared. Okay, so leave out this 2. Now the speed is proportional to what? L. Okay, this is a parameter. The displacement is a parameter. Okay, the displacement is a linear scale and it is proportional to L. Mass is proportional to L cube, and this T, it is T to the power minus 2. So remember this equation, that is F is proportional to L cube into T power minus 1. So William Trimmer, hello, hello, ಕೊಟ್ಟಿ ಎಲ್ಲರಿಗೂ ಯಾರು ಮತ್ತೆ ಬಿಟ್ ಮಾಡ್ತೀರಾ ಬರ್ಲಿತ್ತಲ್ರಿ ಬರೋದು ಬಂದ್ರೆ ಇಲ್ಲಿ ಮಿಂಚುತ್ತೆ So this was the force scaling vector that was defined by William Trimmer in 1989. And this is the table that gives you the relation with other parameters. Okay. So here we have the order, force scale, acceleration, time, and power density. Okay, here in which order means the index. Remember this, the order, it means the index. Alpha in the scaling quantity is the linear dimension. Okay, say for that is L to the power alpha. For example, see how to look into this table. You should go through this. Weight is proportional to volume and volume is equal to L cube. So the order of that is 3. Okay, so the pressure P is proportional to 1 by A, that is acceleration. 1 by A is L to the power minus 2 and its order is minus 2. The positive and negative indicates whether it is a reverse proportional or the normal proportional. Okay, remember this Trimmer force equation, for scaling vector equation, that is F, it is proportional to L1, L2, L3 and L4. Okay, now using those equations, we'll try to have Trimmer force scaling vector. So for example, if power density is represented by P by V naught, if I want to represent this power density P by V naught, then it will be equal to force into displacement divided by T into initial velocity. Correct? Now, P by, remember this, see, carefully observe power density P by V naught is equal to force into displacement by T into initial velocity, that is V naught. Okay, so therefore P by V naught is equal to, what is force? It is L to the power F, and what is displacement? It is L to the power 1. Okay, what is time? So you're required to do the initial velocity 1. So for that, you'll have to refer this equation, L cube L into T to the power minus 2. If you substitute there, you will get the equation for time. Then initial velocity, it is L cube. So if you solve this, you will finally end up with LF to the power 1.5 and L to the power minus 4. Okay, so if I represent that P by V naught will be equal to L to the power 2 power minus 1, L to the power minus 1, L to the power 0, 0.5 and L squared. So that, see here, minus 2.5, minus 1, 0.5 and 2 is represented here in this table. Minus 2.5, minus 1, 0.5 and 2. So this is for power density. Similarly, you should do it for time, you should do it for acceleration, you should do it for force scaling vector. See, force scaling vector L to the power F is what? 1, 2, 3 and 4. So it is 1, 2, 3 and 4. Power density is what? Power density is minus 2.5, minus 1, 0.5 and 2. So therefore it is minus 2.5, minus 1, 0.5 and 2. Similarly, you are required to solve for time and acceleration. Okay. So here there is an example. I hope you would have understood this. You want me to repeat? Okay, we'll continue. So here there is an example. Estimate the associate changes in the acceleration, that is A, and the time t and the power supply P to actuate the MEMS component if its weight is reduced by a factor of 10. So if the weight is reduced by a factor of 10, they're asking us to find out what are the changes in its acceleration, time t and power supply P. Okay. So for that you will be required this table. You are required to memorize this table. Okay, we'll see how to solve it. First, we should have a relation like this. that is the weight W is proportional to volume, that is, and volume is equal to what? L to the power 3. So it involves what? Order 3 scaling. And now from there, that is the order 3 scaling. What is that? So this is the order 3 scaling. Is there any effect on the acceleration? It is 0. So therefore, see here, there will be no reduction in the acceleration. Why? Because for the order 3 scaling, acceleration component is equal to what? 0. So therefore, there is no changes in the acceleration. What is the other parameter they have asked us to find out? Time t. So for the order 3 scaling, the time is varied by zero point 0.5. So it is directly proportional. Since there is a plus quantity, the time is directly proportional. So it will be L to the power zero point 0.5. That is 10 to the power zero point 0.5 means what? Why it is L is substituted 10 here? Because it is factor of 10. Weight is reduced by a factor of 10. So now the linear dimension will be 10 here. So 10 to the power zero point 0.5 means what? 3.16. So 3.16 times reduction in the time to complete the motion. Why there is a reduction? Even though the quantity is positive there, why there is a reduction? Because we are talking about the miniaturization here. Remember, even though the quantity is positive here, it doesn't mean that it will increase. It will decrease. Why? Because we are talking about the term called miniaturization here. Okay. Then what is the other parameter they have asked? That is the power supply P. So what is that? The power supply P. Power supply is zero point 0.5. Once again, L to the power zero point 0.5 is 3.16 times. There is a reduction in the power density. Okay. Then at the last we should state like this: if weight is reduced by a factor of 10, there is a no change in the acceleration. The time is reduced by 3.16 times and the power supply is reduced by 3.16 times. Okay, so this is about the scaling in rigid body dynamics. Followed, I hope you would have understood this. I'll repeat. Okay, we'll have a quick look on that. In the previous session, we studied about the scaling in geometry. Now, scaling in rigid body dynamics. Here, you should know about the terms called forces, power, what is inertia, what is mass, what is acceleration, okay, and what is pressure. Now, these are the basic understandings that we obtain from physics, okay. Then we know that from Newton's second law that F is equal to m into A. And from the displacement equation, we know that S is equal to V naught into T by 1 by 2 into half AT squared. Correct? Now, if initial velocity is equal to 0, then acceleration is equal to 2 into S by T squared. Correct? Substituting this value of acceleration in F is equal to m into A, I'll get F is equal to 2 into S into m by T squared. Leave out this 2. I know that the displacement is a linear dimension, correct? So therefore it is L. Mass, it is L cube. And for time, it is T to the power minus 2. Okay? Correct. Now, so this is the force scaling vector that was defined by William Trimmer in 1989. And this is the order. Okay? Order is nothing but this exponent. Okay? So say for example, if I'll write it here L power 3, then its order is 3. Okay, so the force scaling vector is related to this order is 1, 2, 3 and 4. Okay, for acceleration and time, you can find it out. Okay, how? See, I'll tell you how to find it out. What is T? First, bring this T to LHS. T equals, okay, T equals, or I'll write it like this: T square is equal to 2 into S into M divided by F. So therefore T is equal to square root of 2 into S into M divided by F. Correct? Now square root of 2 you take it outside, since it's a constant, it will have no effect. Now we have square root of S, okay, and square root of M and square root of F. F will come here, correct? So S is linear dimensional, M is L cube, okay, and F is what? L to the power F, okay, which will have 0, correct? Now substitute that, you will get finalized expression like this, that you can write it here. Okay, so they have solved it for power density, that is P by V naught. P by V naught can be expressed as F into S by T into V naught. Okay, so what is F? L to the power F into L power 1 divided by this T into V naught can be expressed like this. Finally, if you substitute, you will get this expression. So you'll have L to the power minus 2.5 minus 1.5 and 2. So these are the orders. Okay, no, these are the exponents. Okay, now these exponents you need to substitute here, minus 2.5 minus 1.5 and 3. So for if this is a third order, you are referring to all these parameters in the third order. So they have given an example. If I reduce the weight by 10, then what is its effect on acceleration, time and power supply? So weight is proportional to volume, that is LQ. So its order should be 3. Now go to this table. This order is 3. Refer all the parameters which is coming in this order. So there is no change in the acceleration. Time will reduce by 0.5 and power density will reduce by 0.5. That is, you will have L to the power 0.5. That is 10 to the power 0.5, 3.16% reduction. L to the power 0.5, 3.16% reduction in power density. Okay. I hope this you would have understood. Similarly, we'll go for scaling in electrostatic forces. See, all the questions here are important. They can be separately asked for 10 marks each. Okay, all these questions are very, very important. And this module is a direct question. Okay, there is no twist and nothing can be asked. Most of the cases they'll ask only the solved problems. So you should remember all these examples as well. Okay. So the third one is scaling in electrostatic forces. And you know that energy U is equal to half into C into V squared, which can be substituted as minus epsilon naught into epsilon R into the width of the plate and length of the plate divided by the separation, that is 2D into the V squared, that is the potential squared. Now if you have this V, okay, this epsilon naught and epsilon r, it is proportional to L squared. Why? Because it's a constant. Then you have only linear dimensions as W and L and T. It is proportional to L to the power 1. Since these are the linear dimension, it is proportional to L to the power 1. Now we have this voltage. Now we need to first consider this voltage, what it is proportional to. So we'll have the linear scaling, that is voltage also proportional to L to the power of 1. Now if you substitute in this equation, that is epsilon naught and epsilon r, you leave it out, W, so it is L power 0, L power 0. For W you will have L power 1, for L you have L power 1, and for V you have L squared divided by 2, you leave it out, for D you will have L power 1. Then you will find it out that U is proportional to L cube. That is, if I change the dimension of this plate by 10 times, then potential energy will change by 1000 times. That is, it will reduce by 1000 times. Okay, I hope you would have understood this. So what is the in electrostatic forces? So what will happen in this electrostatic forces? I hope you would have known this, the working principle of this parallel plate capacitor, right? So whenever the voltage V is applied, then the distance T between these two parallel plates will change, correct? It depends upon the electrostatic force of attraction or the electrostatic force of repulsion. Now, if there are definitely, since there is a voltage applied and there is a distance d, so between the two charged plates, you will have a potential energy between it. And what is that potential energy? It is given by U equal to half into C into V squared, where C is the capacitance. How to derive this capacitance? It is epsilon naught epsilon R into W into L by 2 into D. Okay, now W, L and D are the linear parameters, so it is L to the power 1, and we have considered the linear voltage, so it is L to the power 1. Finally, you will find out that U is proportional to L cube. So if I change the dimension of each by 10 times, then 1000 times the potential energy will reduce. Okay, so similarly you will have electrostatic forces. You can establish the relation between different electrostatic forces. See, you'll have FD, FW, and FL along FW, along FD, and along FL. So there are three kinds of electrostatic forces that can be generated using this potential energy. Correct? For all those three kinds of electrostatic forces, you have this equation, and you'll find out that finally you'll find out that all these forces are proportional to L squared. That is, if the dimension is reduced by 10 times, then these electrostatic forces will reduce by 100 times. Okay, this is the equation for the electrostatic forces in that particular direction. Remember that if you substitute here L power 1, L power 1, L power 2, L power 2, then you will get L power 2. Okay, similarly for FW, FD, and FL, you will get L power 2. So if dimension W, D, and L is reduced by 10 times, substitute in place of L 10. So you will have 10 to the power 2. That is, each of these forces will reduce by 100 times. Okay. So this is what is the scaling in electromagnetic force. So this was about the electrostatic force. Now this is about the electromagnetic force. So for that you need to consider a conducting wire of length L. You know that there will be a force of electric field and a magnetic field perpendicular to it, and definitely that will generate a magnetic force. So that magnetic force is proportional to L power 4. That is, if you reduce the size of this conductor by, say for example, 10 times or by 2 times, then its force will reduce by 16 times. Okay, not much information is given about this. Okay, so what is important is electrostatic force, and for one for the potential energy and one for the electrostatic forces. Okay. Now finally, we'll have the scaling in electricity. Okay, as I said, need not be you need to change what the dimension of the physical object only, like reducing the size of a box or something like that. You can even change physical parameters dimension also, and we can see what its effect will be on the different parameters. Okay, so one such parameter here is electricity. So one such parameter here is electricity. I know that the resistivity R is equal to the resistance R is equal to rho into L by A. Okay, that is, the resistance is proportional to the length and inversely proportional to the cross sectional area, where rho is the resistivity. Okay, now L is the linear dimension, correct? So you'll have L to the power 1, and A is the cross sectional area, so it is L squared. So, and rho is the constant, so it will not have any effect on the linear condition, so it is constant. Take it outside. I have R equal to L by A. So if I substitute here, I'll get L divided by L squared. So finally I'll get resistance is equal to L to the power minus 1. That means if I change or if I reduce the dimension of a thin wire by 10 times, its resistance will, what will happen? It will reduce. Okay, it will change by 10 times. That you need to remember. Similarly, for power loss, you have P equal to V squared by R. In previous slides, we have observed that we have considered the linear scale voltage, that is V proportional to 1. So here also we'll consider the linear voltage. So therefore it is proportional to L squared divided by R, and it should be L. There's some change here. Okay. So the applied voltage, it is V squared by R. In electric field energy, once again half into epsilon E squared. So it should be L to the power minus 2. Okay. Now ratio of power loss to available power P by EB, it is once again L by L cube, which is equal to L to the power minus 2. So these parameters you need to remember. So the current, it is L to the power, this is index, alpha index, okay, it is L squared. Voltage, it is L to the power 1. Resistance, it is, as we have observed here, it is L to the power minus 1. So the index is minus 1. Capacitance is L to the power 1. Inductance is L to the power 1. Power is L to the power 2. This table you are required to memorize. Okay. Say for example, if we change the dimension of a thin wire by 10 times, what is its effect on current? Then you are supposed to tell that 10 to the power 2, 100 times the current will change. Okay. Similarly, that you are supposed to remember. So 100 times the current will reduce. That conditions you are required to remember. Okay. So this is about the scaling in electricity. Now we'll move to the final one, that is, even in fluids you can establish scaling. Okay. So here you have scaling with respect to two parameters. One is the volumetric flow and what is the pressure drop delta P. The volumetric flow is represented by Q. You have a flow in and a flow out. The length of the pipe is L, okay, and delta P is the what is the pressure drop per unit, okay, and what is the volume that is flowing inside this thing. Okay, if the size of this conductor is reduced, will the volume of the liquid that is flowing inside this remain same or not? That we are going to discuss here. So that parameter can be related by this equation, that is the volumetric flow is given by pi into a squared a power 4 into delta p by 8 into mu l. Okay, so if you observe that delta p mu, it will not have much tolerance to this, so it will leads to q proportional to a to the power 4, meaning what? If the size is reduced by 10 times, if the size is reduced by 10 times, then the volumetric flow is reduced by 10,000 times. Okay, this is an important point which you are required to remember. Similarly, for pressure drop, you have this equation. Finally, it leads to the pressure drop per unit length. Okay, is, see, don't get confused. L and delta P is marked same here. Okay, I repeat, don't get confused. L and delta P is marked same here. See, actually, the length of this pipe is L. Delta P, it should be taken for per unit length. Okay, delta P should be taken for unit length. That's why it is delta P by L. And if you observe, it is proportional to a to the power 3. Okay, a to the power minus 3 means what? Minus 3 means, as we have seen in case of resistance, see here, R. Okay, the resistance increases if there is a decrease in the dimension. Correct? That is what is the significance of this minus. Correct? Similarly, here also. Similarly, here also you have a to the power minus 3 means if the area is reduced by 10 times, then the pressure drop is increased by 1000 times. Okay, so this you are required to remember. I repeat, scaling in fluid dynamics, there are only two important points. One is volumetric flow and the other one is pressure drop. Volumetric flow is represented by Q and it is proportional to a to the power 4. Pressure drop is proportional to a to the power minus 3. So if there is a reduction of the pipe by 10 times, length of the pipe by 10 times, then the volumetric drop is reduced by 10, volumetric flow is reduced by 10,000 times, and the pressure drop per unit length will increase by 1000 times. Okay, so this is, even in heat you can find out what is the significance of scaling. Okay, so you have conductivity, okay, and how fast the heat can be conducted. So that two parameters I leave it for you. Okay, so you have the thermal conductivity K to be equal to this equation and it is proportional to L to the power 1. So if the scaling is done by 10 times, that is, if we reduce the size by 10 times, and the thermal conductivity is reduced by 10 times. Similarly, the time required for transfer of heat, that is F naught by alpha into L squared, it is proportional to L squared. So definitely, if the size of the conductor is reduced, then the time required to transfer the heat will increase. is also reduced. Sorry, it is also reduced. By what amount? That is 100 times the time required to transfer the heat from one end to another end of the conductor will also reduce. Okay, so this is what we discussed in scaling laws. So this is the overview of the chapter. All the questions are important. Scaling in geometry, scaling in rigid body dynamics, scaling in electrostatic forces, electromagnetic forces, electricity, fluid mechanics, and heat transfer. So you'll have some of the important questions here. You can observe here. Explain scaling in heat transfer, wherein you are required to write this. Okay. Then estimate the variation of the total heat flow. There is one solved problem. Okay, you just have to estimate the total heat flow of the time required to transmit heat. That is, the time required to transmit heat is given by T equal to F naught by alpha into L squared. You should be knowing that T proportional to L squared. If the factor is reduced by 10, so it is 10 to the power 2. So 100 times the time will get reduced. In fluid mechanics, you are required to write this. Okay. Two important parameters, volumetric flow and the pressure drop per length. Using scaling laws, estimate the variation of volumetric flow. Once again, there is a direct formula here. Just estimate it and then find out and tell that it will reduce by 10,000 times. Remember, if it is 10, if we change the value by 100, then it is 100 to the power 4. So remember while substituting. Then obtain the scaling laws for rigid body dynamics. Once again, you're required to and tabulate it. You are where you are required to derive this equation, and then rigid body dynamics, and then you are required to write this table. Okay. Associated changes in time. We have solved this question. Okay. So once again, discuss scaling in geometry in detail, which we have already solved. Finally, this is what the electrostatic force. What will happen if it is individual forces if it is reduced by 10? So it is simple. You have this equations here for electrostatic forces, and you know that it is L squared, L squared, and L squared. L squared, L squared, and L squared. So if it is reduced by 10, then 100 times each force will get reduced. So even if you remember the formula, you directly don't write here, it is 100 times. First, you're supposed to write this diagram equation, and then you need to establish this relation, then substitute and then state this answer. Else you'll lose marks. You know VTU, right? Then discuss scaling in electrostatic forces in detail. Okay. So for that, electrostatic forces, you are required to write this equation. Then write a short note on scaling in heat conduction and heat convection. Okay. So this is what you are required to write. Okay. So we have discussed the full module 4 in this. Okay. And module 5 video is there in the YouTube channel of EC department. Okay. We'll also upload this module 4. Okay. I hope you would have understood. We'll also upload this module 4. Okay. And please, you can ping to us like in next session which module you would like to know. Then we'll discuss that module in our next session. Okay. Thank you.